In a second. Yeah.
Okay, so to the people watching on YouTube, you missed this. This is how I'm increasing student retention in this class because yes, just a warning to the students. This class will be like I think harder than the previous two classes. I'll be doing harder examples. So don't get intimidated. Okay. So I really just want to like cover two main things. Wait, Hmm. Well, invariants and monovariants. Oh, my handwriting is as good as ever. Wait, gotcha. Okay, I'm not really able to read chat right now. You will have to like just unmute. Okay. Uh, maybe colorings, but like I think just invariants and monovariants probably. Okay, so just combi doesn't really have that much theory, so I'll like just take 5 minutes to tell you the definition of an invariant, and then we will do problems. Okay. So in fact, I'll just introduce what an invariant is through a problem. So suppose you have like a bunch of numbers, 1, 2, 3, 4, 5, and 6. You have 6 numbers written on the board. Suppose you can like at any point say add 1 to a number and like pick two numbers, add 1 to one of them, and subtract 1 from the other one. Okay. So I can make it like so from 1, 2, 3, 4, 5, I can go to 1, 3, 3, 5, 6, and like just do those moves, right? Can I ever end up with just 1, 2, 3 written on the board? Where's the chat?
Can you repeat, please?
Are you making this? Right. Of course not, right? I just said there are like 1, 2, 3, 4, 5, 6 written on the board. In a move, I add 1 to one of the numbers and subtract 1 from another number. I can make as many moves as I want. Can it ever be that I end up with only 1, 2, 3 written on the board? Obviously not, because there were 6 numbers and now there are 3 numbers, and there is no way to decrease the number of numbers. So the point is, in any moves, the total number of numbers written on the board, that's always 6. That doesn't change. Right. So there's no way I can get to only 3 numbers. So the total number of numbers written on the board never changes. Like because R moves does not allow us to lead a number. So that is an invariant. And that is the definition of an invariant. Yes, people are saying sum remains same. That doesn't even matter. Have just decreased the number of digits on the board. Yeah. An invariant is just something that does not change. So in this case, well, the total number of numbers on the board doesn't change. Of course, most problems will not like be this trivial. Now, like, tell me, can I ever end up with, say, 2, 3, 4, 5, 6, 7 on the board?
No, you can't.
No, no. Why? And as people have already pointed in the chat, it's because I'm adding 1 to something and subtracting 1 from something else. So the total sum of all the numbers does not change, right? And in this case, it has changed. It has increased by 6. So this is not possible. So this is like a slightly less like obvious example of an invariant. The total sum of these numbers doesn't change. Okay. Someone has found the Miro. I do not. It's fine. No, is that Miro or is that someone writing on the Zoom? I don't care. Okay. So what's a monovariant? So an invariant is something that doesn't change. A monovariant is something that does change, but only in one direction. So it always increases or it always decreases. So for example, like for like the most trivial example you can think of, suppose I have like 5 and 6 written on the board. In any move, okay, let's start with the same thing. 1, 2, 3, 4. I have 1, 2, 3, 4, 5, 6 written on the board. In any move, I can subtract 1 from any number. This time there is no addition. Can I ever end up with 1, 2, 3, 4, 5, 6, 7? Oh, sorry, no, sorry. 1, 2, 3, 4, 5, 7. Yes, Eamon? You get
Bhaiya, I have a doubt. Can I ask it?
sure. Just unmute and ask.
In the first problem, if we subtract one from the first one and add
Yeah.
one to the to another number,
Hmm.
then we will have 5 numbers.
What? No. Zero is still a number. Zero is still written there. I'm not getting rid of zero.
Oh, okay.
I should have clarified that. Okay. Anyway, so 1, 2, 3, 4, 5, 6. You are only allowed to subtract. Can you ever get to 1, 2, 3, 4, 5, 7?
No, you
Once
can't
again,
because the
obviously not, because you are only decreasing.
No.
You cannot increase. Right. Uh, but monovariants are slightly have like one more use other than this. Like for invariants, you just like use them to show that you cannot get from one state to the other. Monovariants, you can also use one more thing. Say you can show that some process always terminates. Like let me guess. Let me just see an example. A second. Mm. Okay, sure. Let's just start with something simple. Okay, suppose I start with two positive. Here's example one now, slightly sophisticated, although still. Let's see. Okay, suppose you have two positive integers a and b written on the board. Okay, now yeah, in any move you take the larger number. Suppose in this case it's yeah two positive integers on the board. You take the largest number, say a. You get rid of a and you replace it by a minus b absolute value, and then you do it again. So you take two numbers. Well, basically, you like okay, since a is the larger number, this is just capital A minus b. So in any move, you take the bigger number, you subtract the smaller number from it. The question is, uh, sure, and you do this till one of the numbers doesn't become zero. Like if they are positive integers, then you take the larger, subtract the smaller until they become equal. In which case, you just end up with a zero and then you stop. Can this process go on till infinite? Like, will we? Is it necessary that we stop?
so if both of the numbers have to be positive, then obviously it will stop because they will eventually become negative, right?
No, they will not necessarily become negative, right? Because something is always like, why would they become negative?
Oh, sorry. You would eventually go down to zero.
Yeah, exactly. The point is that we are decreasing the numbers, and like this is not like real numbers where you can go from one to half to one third and so on. Any decreasing sequence of natural numbers, it always stops somewhere, right? For if these were real numbers, then this is not necessary. You can make it like if suppose you start with root 2 comma root 3, then this process goes on forever. But since these are positive integers, subtracting them always gives a positive integer. This process stops because there is no infinite decreasing sequence of positive integers. Okay, is that clear? The first example was invariant.
Can you explain the root 2 comma root 3 part again?
Okay, like okay, wait, how do I explain? So here for positive integers, we have a decreasing sequence of positive integers, right? And this stops.
Yeah, I understood it for positive integers.
This actually does not stop. Like I'm saying, just in problems, you have to specifically say it is because these are positive integers that this stops. If you take root 2 and root 3, then what will happen? You have root 2, then root 3 is bigger, so you subtract. Then root 2 is bigger, so you subtract from here and you will get 2 root 2 minus root 3. And then this is bigger. Well, actually, I don't know which is bigger. I can't do that in my head. But the point is, these two can never be equal because root 2 and root 3 are irrational numbers. Like, okay, the formal proof is like slightly weird. I'll not do the details right now. But the point is, since like root 2 by root 3 is irrational, you can never like Like the thing is, the process stops when something becomes zero, right? Because we are always subtracting small from big, so it cannot become negative. So it has to become zero, right?
Yes.
So, and since we are always like some combination of root 2 and root 3, we'll end up with like a root 3 minus b root 2, or b root 3 minus a root 2, right? Oh wait, this is not what I'm saying, sorry. Or
Is it
a
necessary? Is it necessary for them to become zero?
no. If the process stops, they have to become zero, right? Either
Oh,
the
okay.
process doesn't stop, in which case it doesn't stop. I'm trying to show why it doesn't stop. So assume it does stop, in which case something becomes zero, right? But the reason that's not possible is because any number is of the form a root 2 minus b root 3. And suppose this is zero. So like rearrange a root 2 equal b root 3, divide by root 3. So this is an integer, and this is an integer times an irrational number. So like this side is irrational, this side is rational, unless both a and b are zero. But you can prove that a and b both are not zero. Like, just trust me on this, I would say. But this is basically the point. Okay, can I do this better? Like, the idea is that this algorithm is basically like taking the GCD of two numbers. If you remember, suppose you have two large numbers, say 12 and 20. Then from the bigger, you subtract the smaller, and then you do it again. Then you do it again. And then you do it again. And now 4 is the GCD, right? Does everyone know the GCD algorithm?
Yes.
Does anyone have any question? Was this covered in the intro NT class by Sai? There's no one here. Anyway, this is not the point. You can just ignore the root 2, root 3 example for now. I was just saying that like proving it's infinite will take like a bit of more work, which is not the point of this lecture. Let's move past this. Is everyone clear what an invariant and monovariant is, and how a monovariant can be used to prove a process terminates?
Yes, sir.
Okay, so that is basically all the theory. So now let's move to some examples. So let's start with okay, let's start with something. Suppose the numbers 1, 2, 3, 4, okay, all the way up to 16 are written on the board. Okay. In one move, what you do is you pair up the numbers. So there are 16 numbers, you make 8 pairs. So suppose you pair up 1 and 2, 3 and 4, 5 and 6, and so on. And then in any pair, so 1, 2 is a pair, you erase both the numbers and you write the absolute value of their difference on the board. So if I paired up 1, 2, 3, 4, 5, 6, and so on, I will end up with 8 copies of 1, right? And then once again, you pair up the numbers, you take their difference and take the absolute value. So in this case, you'll just end up with 4 zeros. And then you do it again. So from now you'll have 2 zeros, and finally you'll have a single zero. So now we end at a 0. So the question is, what are all the possible ending values? Is the question clear to everyone?
Yes.
Just ask if the question isn't clear. I'll like give you 5 minutes, like some time to try it.
Can you please just repeat the question once
Okay,
again?
sure. So you have the numbers 1, 2, and all the way to 16 written on the board. Okay. In a move, you pair these up. So in the first move, you will be making 8 pairs. And then what you do for any pair A comma B, you replace it by a single number, A minus B, absolute value. So at first you have 60 numbers written on the board. You make 8 pairs, you'll have 8 numbers left. Then you'll have 4 numbers left, then 2, then 1. What are all possible values of this number, this final number? Is the question clear now?
Yeah, thank you.
Okay.
Can we try parity?
Yes, that is a good. Yes, you can do that.
So, like,
Just
for example,
hmm,
A
go on.
minus B is congruent to A plus B mod 2. So the parity of the sum has to remain invariant.
Yes, yes, perfect. Okay, so wait, I'll just give you like 1 more minute so that everyone can like think about that, and then I'll explain. Also, for that, like now try to find the construction for all those numbers, because you also have to do that. I'll explain that what he said. So what he basically said was this. This okay, first of all, can everyone okay. Plus 1 equal minus 1 mod 2, right? So A minus B doesn't matter, like it's either plus A minus B or minus A minus B, but both of them are equal mod 2. So it is just mod 2, it's just A minus B. And once again, minus and plus are the same mod 2. So this is just A plus B mod 2. Is everyone clear why this is true? A minus B mod equal A plus B mod 2. Please repeat. Okay. So what he said that uh but the A minus B and A minus B absolute value and A plus B are equal mod 2. Like whoever said the solution, Keshav, I think.
Is it true for any modulo M or just 2?
No. No, just 2. The thing about 2 is plus 1 equal minus 1. Right, because 1 is odd and minus 1 is odd. They're both odd.
Got it. Thank you.
So the thing is, mod is either like just the number, like mod A minus B will either be just A minus B or it will be B minus A. And but minus is same as plus, so this is equal, this is the same as A plus B, and this is also the same as A plus B. Because you can just make minus plus and you can just exchange subtraction and addition mod 2. Odd minus odd is even, odd plus odd is even. Even minus odd is odd, even plus odd is odd. So okay, so everyone understands why this is true, right? Okay. So now, how do we use this to do the problem? So at any point, we are replacing. So earlier, what we had was we had this, like in this example, when we were adding one here, subtracting one there, we had the sum of the numbers was the invariant. Now the sum is no longer the invariant. Like the sum, the sum decreases. However, the sum, if it was even, it stays even. If it was odd, it stays odd. because if we have A and B, their sum is A plus B, and we replace it by A minus B, which is the same as A plus B mod, right? So in this entire process, the sum of the numbers does not change mod 2. Does everyone understand that? I should ask, like, does anyone have any questions? You know? So, okay, what is the sum of 1 to 16?
8 into 70.
8 into 17. So this is even, right? So what can you say about the final number?
It has to be even.
It has to be even, correct? If I remember. If I'm right, congruences is only about remainder and A minus B, like how we use it here, or maybe lack of this. I'm not exactly sure what your doubt is. Did you attend my like congruence class, like in T1? You can ask after class. Like, of course, okay. Yeah. So does everyone understand why the last number must be even? Right? Okay. So now we are not actually done with the problem. We have proven the last number must be even, but there are like a lot of even numbers. So can the last number ever be 18?
I'm sorry,
Hi,
can the last number ever be?
what?
What was your question?
Can we have proven the final number is even? Everyone understands why that is, right? Yeah. Can the final number ever be 18?
No, because sum is decreasing.
No, that is not enough. The initial sum was greater than 18. Yeah, I'm doing this to increase student retention. I think it's working. But you have to like it is the final number being 18, you actually don't need like any invariant or monovariant theory. No, I'm just waiting for someone to answer why the final number can't be 18.
Because we are subtracting them, and
Yeah,
the maximum
exactly.
number is 16.
Maximum number was 16. It can never become bigger than 16. Similarly, can it ever be minus 2? No, because we are always taking absolute values. So we can never end up with a negative number. So we can only have even numbers between 0 and 16. Can it ever be 16 itself?
No, same argument again.
Same argument, yes. In the first step, we have 16. We'll subtract something from 16. So everything afterwards will be less than 16. So we basically just have 0, 2, 4, 8, oh wait, 6, 8, 10, 12, 14. Right. So these are the numbers that are left. These are all the possible numbers it can be, right? Now you can. Hmm? Okay, sure. Yeah.
Can't we also show that 14 is not possible?
How?
So you take in the first step, suppose we are trying to keep the maximum number possible in the board. So then you would need to subtract 16 and 1. You would need to pair up
Okay.
16 and 1, right? So
Yes.
you do that. So you have 15 on the board. And then
Yeah.
suppose you also pair up 2 and 3 to keep another 1 for the next step.
Sure.
So now you have 15 and 1.
Okay.
So then in the second step, you subtract 15 you subtract 1 from 15 and you're 14. And you
Yes.
keep on trying to reduce the maximum number on the board.
Okay. And you're saying then it will become 13 and then 12. And so
Yeah, kind of. And because the number of
yeah,
total steps is known, we can sort of bound it.
the number of steps is 4, and so it will must end at 12. Okay, so a little bit of a story. Can you do sentence? When I do the next mono question, I'll tell. This is just an invariant question for now. Yeah, right. Yeah, I will. Okay. Yes. So Keshav, now I'll tell you an interesting story. So this problem is actually from IIT Bombay Math Olympiad 2025. So like I actually went there to give this Math Olympiad. And so I saw the invariant. I'm like, okay, so it has to be same mod 2. And so it must be one of these numbers. And due to your argument, it has to be like less than equal to 12. So it's probably, and then I found ways to get 12, 10, 8, 6, 4, and 2, and 0. So I said, like it was an MCQ based paper. They said, how many possible final numbers are there? And so I picked 7. I was wrong because you can also be subtracting 0 from 14.
Oh, right. You can have two
Don't-
ones. Oh,
I made the same mistake in contest, so don't feel bad, but yeah. Okay, so 14 is actually possible. Can someone tell me how you'll construct 14?
What was the argument when we determined 12?
No. That argument was wrong. Like argument was that largest number on board is 16. Every move we are subtracting something from 16, right? So in the next move, the largest number will be at max 15. In the next move, it will be at max 14. In the next move, it must be at max 13, after which it will be at max 12. Like, since we take at least 4 steps, the largest number must get down to at least 12. This was the proposed argument. The reason this fails is because while you are subtracting something, you can just be subtracting 0. Please increase brush size.
Can I answer the construction problem?
Sure. Wait, just give like some more time for everyone else.
Yeah.
Wait, how do I increase brush size? Oh, okay. Is it better now? Less, little more thing. Even more than this. This might be okay. There's a sign. What was the last question? This is the only, yeah, the question I asked. Okay. So we have proven that anything except 0, 2, 4, 6, 8, 10, and 14 cannot be made. These are all the possible, like anything else we have proven can't be made. Now we have to show that these can be made. Like, okay, I'm just telling you the answer that all of 0, 2, 4, 6, 8, 10, 12, 14 can be made. So the invariant parts of the problem is over. Invariants can be used to prove that something cannot be made, right? We proved odd numbers can't be made, and then we also proved negative numbers and numbers bigger than 14 can't be made. Now we have to prove that something can be made, and you cannot do that by invariance. For that, you have to like actually show an algorithm that ends in these numbers. Like there are two parts to this problem: showing that nothing else can be made, and then showing that these can be made. Does everyone understand? You just, I'll just that. Does everyone understand what we are trying to do right now? If anyone has any questions about that, then just ask. Otherwise, just just try to do something. Like, okay, first of all, try to construct 14. How will you make 14? Like, give me a sequence of moves that ends at 14. Okay, Keshav, you can say the answer now.
Yeah.
Also, go on, just go.
Yeah. So basically, the idea will work for every other number as well.
Okay,
So what we try to do is we try to create the number 14 and then a bunch of zeros.
okay.
So that every time you're subtracting a zero and just 14 stays on the board.
Hmm.
So for example, in the first step, suppose we do the same thing, right? Suppose we take
Hmm.
16 and 1. Suppose we pair up 16 and 1.
Hmm.
And then everything else we just do adjacent. So we have a bunch of ones.
Yes, that okay, that's it. You have the idea. I'll
Yeah.
okay, I'll just give everyone else like I'll just wait for everyone else to like digest that before I like explain the all the details. So okay, think about this. Like for for 14, what he's proposing is like pair up 16 and 1, and then pair up 2, 3, 4, 5, 6, 7, and so on. Right. So 16, 1 becomes 15. All of these become 1. Right. Then you pair up 15 and 1, you get 14. And then you pair up the rest of the ones, you get zeros. And after which you will just get 14 because it's just 14 and zeros. That's what I was doing. Yeah, very good. Yes. This is how you this is how you can get 14. This is now just think about how you can extend this to get every single number. Like the same sort of idea works, but just modify it a bit. Till that, I'll also like look for the next problems.
Will it be like that we pair up 16 with any number and then we pair up the consecutive terms so that we can get one and in the next step? Yeah.
Perfect. Well, exactly. So, okay, not any number. Like the thing is, if you pair up 16 and 2, then like you can't pair up 1 with 2 because you're already used to. But you pair up 16 with some odd number. So like 3, like if you pair it up with 3 or like 5, okay, you pair it up with 3, then you pair up 1, 2, then 3 is not there, then you pair up 4, 5, and all the way. So you'll end up with 13 and a bunch of ones. Then you'll get 12 and a bunch of zeros and then just 12. So suppose you want to get to say, yeah, so basically 16 1 gives you 14, 16 3 gives you 12, 16 5 gives you 10, and so on. Like you pair up 16 with some odd numbers and everything else you do consecutive. Uh, Iman, I assume this was what you were like going to say. I mean, you basically said that. Is the idea clear to everyone else? It's- You said it. Yeah, I was like, was this what you were going to say? But you had already said it. So, okay. If anyone has any questions, just ask. Otherwise, I'll just give like some notes. So, this is sort of how like a normal invariant problem will look. Well, first of all, like there will be some process that like you start with a bunch of numbers and you end at a single number. And the question asks you to find what are all possible values of that number. So first you have to, well, first you have to like find some invariant, which will tell, sometimes that invariant will just tell you what the last number is. For example, okay, I'll give you an example for that later. Sometimes it'll just tell you what the last number is. Is J combinatorics enough for IMO? Okay, so we have a troll here. You know that what tomorrow there was double of today's. Yeah, because I think Sophie people also joined. A lot of people like wanted just IOQM tip specifically. And also there were 2 lecturers, so double students. Yeah. Anyway, what I was saying. So yeah, you'll start with a bunch of numbers, you end up at a single number. You use some invariant to find like some possible values of that number. Right. And then you have to like show that those numbers are actually possible. Yep. Like these are both important steps. Like first showing that nothing else is possible, then showing those are actually possible. I think that is clear to everyone. Is any questions just ask, otherwise I'll just do the next problem.
I think for 12, 14 comma 1 also works. And similarly for 10,
Yes,
12
that
comma
is true. You can also do that. You can go the other way. There are a bunch of other constructions also. Yeah, 14 comma, like instead of like here I fixed 16 and I was changing this number, I can choose the other number also. Yes, exactly. Like you, as Online History Club said, you cannot check all the natural numbers from 1 to infinity. So first you like do some invariants to like reduce to finite advantage of cases. And yeah, Sophia I'll talk about later, whatever. To reduce to finite amount of cases, and then those cases you just individually construct. Or sometimes you might have to do more things. Like here you might also think that 16 is possible. Like our invariant doesn't immediately tell us 16 is not possible. So you say it's not possible and remove it. Okay. Anyway. So okay, this was like a problem where you also have to do the construction. Sometimes you just won't have to. Say, for example, you have the numbers. You have the numbers 2, 3, all the way up to say n written on the board. In a step, you pick two numbers, A and B, and you replace them by, just remember, AB minus A minus, no, sorry, AB plus A plus B. Yeah. You take any two numbers A and B, you replace them by AB plus A plus B. So clearly, like the number of numbers decreases. So you had n minus 1 numbers to start, then you'll have n minus 2. Eventually, you'll be left with a single number. What are all possible values of that number? Is the question clear to everyone?
Can you please repeat the question?
Okay, so the numbers 2, 3, all the way up to n are written on the board. You pick two numbers A and B, you erase them, and you write AB plus A plus B on the board. Eventually, you'll be left with a single number on the board. What is it? Why did I? Okay, I don't know why I excluded one, but it's fine.
Yeah, I think I got the invariant.
Okay, just let everyone else do. You can, Keshav, just DM me your answer in the chat.
All right.
I'll also like give a different problem for you to try it then. Please repeat one more thing. It's fine. Okay, okay. You have the numbers 2, 3, 4, 5, 6, all the way up to n written on the board. Okay. In a move, you take two numbers. Say you pick 2 and 5. You erase 2 and 5 and you replace it by 2 times 5 plus 2 plus 5. So 17. So first you had 2 to n. Now you have 3, 4, 6, all the way to up to n. You have removed 2 and 5 and you have added 17. You keep doing this until there's a single number left on the board. What can that single number be? Is the question clear?
Yeah, it's clear now.
Okay, good. Then we do stuff with that. Okay, Keshav, just tell me what the final number is. Hmm. find the answer in terms of n. Obviously.
So I mean, here we're assuming that this is true. Because,
What?
no matter how we choose the numbers, we'll still get the same end result.
Okay, no, actually, I shouldn't have like spoiled that. I mean, it is true, you get a single, but like, don't assume like, okay, the question says find all possible values, but there does end up being a single possible value. You have to prove that though, that you're not assuming that. Kesha, just tell me what the answer is. Your idea is correct. Hmm. Yeah, okay. Yeah, that's correct. I'll give like some more time for other people to try. Till then, I'll just write another problem for like people who are done. Let's see.
So what basically you are saying that you choose a pair A and B and
Hmm.
replace it with AB plus A plus B. Then you
Yes.
remove A and B from this board and you
Yes.
add the new number we obtained.
Yes.
So what was the question that
What's the final number?
what is the final value?
Okay. These are like enough invariant problems. I'll give a like first do this problem. For those who are done, you can try this problem. This one is monovariant. Uh, okay, so we have the number line, 1, 2, and so on. On some like there are finite amount of stones placed on a few places. Like suppose there's one stone at 1, 2 stones at 2, like nothing at 3, one stone at 4, and like some configuration. I like do not care which. Can you do a solution? I'll do like I'm just waiting for some more people to try. I'll do the solution later. I'll just I mean yeah. Okay. So what you do in a single move, if you can what you can do is if some position, like say here in this case 2, has at least 2 stones, you get rid of them and you place one stone to the right, one stone to the left. Like if it had like 3 stones, then you just remove some 2 of them, you place one here and one at 6. Okay. And you keep like you do this as much as you want. The question is, can you end up where you started again?
The number line extends on both sides, right?
The number line extends on both sides. By the way, does anyone have any ideas for the previous question?
With observation, I'm getting sums of products of the numbers taken one at a time, two at a time, and so on. I'm not sure if it's correct, but I've gotten it for 4 numbers still.
Wait, that's interesting. Does that actually work? That is not the invariant I thought of, but that might work. Let me think. Yes, yes. Iman, your idea is correct. Yes, that is exactly it. You can try the next problem. Wait, what were you saying? The sums of let me just think if that also works. Oh wait, that actually might actually work. Yeah, we are doing invariants and monovariants only. I'll just tell you the problem. Wait. No, Iman, that's not exactly the answer because number one, I removed one from the set. Just like so many people. Yes, Suryadeep, your answer is correct. Okay, enough people have given me correct answers. I'll just now explain the solutions. Okay, so the thing is to notice that AB plus A plus B. No, Iman, your answer is still incorrect. Your idea is correct, but I think you're messing up the calculation. Yeah, AB plus A plus B can be written as A plus 1 times B plus 1 minus 1. This is also like called Simon's favorite factoring trick. Okay, no, Zayad, you're almost correct. Not quite. I'll get to it. Okay. So AB plus A plus B is A plus 1 times B plus 1 minus 1, right? So what you have is the product of the numbers doesn't change. Like not the product of the numbers, the product of the numbers plus 1. How do you see it? I'll get to that also. Okay. So the product of the numbers, at first it's A plus 1, B plus 1, C plus 1 all the way. Now you have replaced AB. You have gotten rid of these two things, but you have added A plus 1, B plus 1, minus 1. So the product is still the same, right? Does everyone see why the product is same? Yeah, Iman, your answer is correct now. The factoring algorithm. Does everyone see, first of all, why the product of A plus 1 doesn't change? If anyone has any questions, just ask.
So these ABCs are the numbers written
Yes.
at that
Like
step.
take all the numbers written on the board, add one, and multiply them. The answer is a constant. Right. So initially the answer was n plus 1 factorial by 2 because you add 1 and you get all the numbers from 3 to n plus 1. I have removed, like, their product should be n plus 1 factorial, but for some reason I removed 2. Like it starts at 3. So it's n plus 1 factorial by 2. And if the last number is x, the product is just x plus 1. So x plus 1 equal n plus 1 factorial by 2, x equal n plus 1 factorial by 2 minus 1. Okay, yeah. Okay, does everyone see that? Why does everyone get this proof? Can you repeat? Sure, I'll repeat once. Okay, the first claim is the product of all the numbers like xi plus 1 is invariant. And since the product was initially n plus 1 factorial by 2, finally it is that. And hence x must be this. Nikhil, I'll answer your questions after class if you have anything else. Anyway, I'll just show you the next question. Wait, I'll just first show the next question, then I'll get to how I saw the factoring. The next question I'll repeat is that what are we actually doing at least? Okay, I'm 1729. We are doing problems right now. I like explained invariance and monovariance theory. I'll just tell what problem we are doing, then like I'll explain invariance and monovariance again for you if you want. Okay, the problem we are trying right now is this. So you have a number line, and on the number line, some finite amount of stones are placed. That's fine. Like you can be like slightly rude. I don't care. Yeah. So on the number line, there are. Wait, were you saying I wasn't? Don't know. Anyway, on the number line, we have some finite, like extends in both directions, like 0 and all. We have some amount of stones placed. So at 1, I have placed a single stone. At 2, say I have placed 3 stones. I have placed nothing on 3. On 4, I have placed 1. On 5, I have placed 1, 4, 3, 4 stones, or whatever. In a single move, I take some place which has at least 2 stones. I remove 2 stones, and I add 1 stone to each of its neighbors. So from 2, I remove 2 stones. I add a stone to 1. I add a stone to 3. from 5 I remove 2 stones, I add 1 to 4, add 1 to 6. Is it possible that I end up like I do some sequence of moves and I end up back where I started?
So after you choose a particular number which has at least 2 stones and distribute the stones to the neighbors.
Hmm. I'm sorry, I didn't catch your question. Can you
After
repeat?
you distribute the 2 stones to its neighbors, which number will go to next?
What? Which?
In this process that you have described, we in the start we choose any number which has at least stones. We go to it and we distribute 2 stones of it to its neighbors, right?
Yes. Yeah.
After that step, which number do we go to next?
It's up to you.
Okay.
You can go to whatever number you want. Can you end up where you started?
Okay, but like if I have 4 stones in one particular number, I can just choose that number twice and
Yeah. The question is okay. Okay, the answer is no. You have to prove that no matter how the initial stones were, no matter how you do the moves, you can never get back to where you started.
What is the initial configuration?
Can be anything. The question is just for any initial configuration, prove you cannot get back to where you started.
Okay.
Okay. Okay. I'll quickly just say how I saw the fact. And if anyone is still unclear about the question, just ask. I'll just answer the question how I saw this factorization. So this is actually like the sort of factorization you will see a lot. If you ever see, say, xy plus, say, p times x plus q times y, this is like called Simon's favorite factoring trick. What you do is you add pq and you subtract pq, and then you notice that this factors as x plus q times y plus p. Simon's favorite FSFFT. I do not know why this has a name. Okay, I'll also re-explain that. While everyone is trying this question, I'll just go back and explain people's doubts. Yeah, this is just like a very common factoring trick, which like you'll see often enough that you should just like, whenever you see like product of two numbers plus linear terms in those numbers, you can just try applying this. It might help. And okay, there's also like a version of this something here, but yeah, that's like I'll just say the more general thing. AXY plus BX plus CY equal AX plus C, AY plus B by A. SFFT. This is you didn't miss me. We're just doing problems today mostly. There's really no theory in combi. But okay, this like the point is you multiply like you once again you multiply and divide by A to get A square here, and then you just work with AX and AY instead of A and Y, X and Y, and then it becomes just what it was earlier. Okay, I'll also like re-explain the solution of the previous question for those people who joined late. Okay, I will read your solution later. Yeah. So they will just be problem solved because combi, like, okay, until you get to graph theory, there is no theory. Okay, that's not exactly true, but there's very little theory. Yeah, okay, so the previous question, the thing is this. So initially you have 1, 2, all the way to n, right? Add 1 to every number. Oh, sorry, we don't have 1. Add 1 to every number. So you have like 3 to n plus 1 and multiply them and write down the result. So the result in this case is n plus 1 factorial by 2, right? Now, suppose you do this like step of the algorithm. you take the numbers 2 to n, you get rid of some a and b. So you have 2 all the way to n, and a and b are removed from the set. How should I say? Minus a comma b. And you add ab plus a plus b. Whatever, don't mind the notation. Anyway, now you just look at the numbers written on the board. So you have 2, 3, all the way to n, but a and b aren't there, and you have ab plus a plus b. Once again, do what you did. Add 1 to every number. So you will have 3, 4, all the way to n plus 1. And then you'll have ab plus a plus b plus 1. And now multiply them. I say you will still get n plus 1 factorial by 2. The reason is when you multiply like all of these numbers, you get n plus 1 factorial by 2 by a plus 1, b plus 1, because a plus 1 and b plus 1 are no longer part of this list. And then you multiply by ab plus a plus b plus 1, which is just a plus 1 times b plus 1. Cancels, cancels. And then you use the same argument. Once again, you get rid of 2 numbers, you get ab plus a plus b, ab plus a plus b. The product after adding 1 is still n plus 1 factorial by 2. And it will always be n plus 1 factorial by 2. Online history club, is that clear? Oh, that's the country mascot, Anirudh. We were given. Everyone doesn't have it. We only had 5. Anyway, online history club. You asked it out of like asking previous solution again. Do you understand this?
Yes, understood.
Okay, good.
So in the second question, you are saying, is it possible to reach the starting configuration of the stones, right?
Yes.
Okay, okay.
Wait, where was the question written? I have lost the question, guy. Here. I don't understand. Nikhil, I can I'll answer that like after the class. I'll be here for like questions afterwards. I'll like discuss. Okay, let me just, some people have like send me some things for question too. Let me just read through them. So Keshav. Two. Keshav, that's intuition. You need something more concrete. Really nice. This is not a headband. This is a bunny ears. I'm doing this to increase student retention. I think it's working. Students seem more interactive today than my previous classes. I think can I qualify? Wait, someone else also sent me something. Oh, yeah. What is this? Yeah, I'm reading your answer. When you subtract two. No, you can. No, I don't understand what you're saying. Why is combi damn hard? Combi is. I mean, okay, it's like personal opinion, depending on aspect. Like, yeah. I mean, there's no objective ranking. So I also like combi is one of my weaker subjects, but if like they had even yeah, okay. The thing is, someone's like doing some parity argument. The issue is like, suppose you have 2 stones here and like stone here. You can like wait. I'll just type what VMs with.
So in this new question, can you try to construct a function that like decreases or increases and then say that it doesn't?
Yes. Yes. Perfect. Find some monovariant and prove it always increases or always decreases. So you can never get back to the same value. Let's see. You repeat the question once. Okay, sure. You have a bunch of, you have the number line. On every number, some amount of stones are placed initially. So any amount. And the total amount of stones is finite. And in a move, you take a number where, go to a position where at least two stones are placed. You remove two stones and you add one stone to each of its neighbors. And you do this as many times as you want in any position as you want. Is it possible that you eventually get back to where you started?
The total number of stones is finite, right?
Total number of stones is finite. I wonder is I think the problem might still be true for infinite, but I'm not sure. Have to think.
I mean, if you plot the numbers on like the number line, the number of numbers would be infinite, right? So like the number of
What?
stones can how be
No,
finite?
no. Like eventually there are no stones. Like suppose in this configuration, 1 has 2 stones, 3 has 1, 5 has 2, 4 has 2, 6 has 1000. Then 7 to infinity, there are no stones. By 0 to minus infinity, there are no stones. Total finite.
I think I figured it out with the function idea.
Okay, like send it to me in like private chat.
Yeah.
The answer. By the way, by the way, 1729. Do you understand the question we are doing? And like, have you seen invariants, monovariants before? Is the answer 1434? It's a yes no question. It's actually a proof question. But yes, the answer is 1434. The answer is always 1434. Someone send me an image in private chat. This will take a while to read. Perfect. Yes. Suryadeep, it is correct. You have solved the problem. Okay. I'll give some hint. So, in some sense, you're making the you're making the stones more spread out. Earlier, the stones are concentrated, now they're becoming more spread out. Right. You want some way to formalize that idea. Right. Can someone give me an example of something that like becomes smaller as you spread it out more? Uh, Hint, it's related to my last class.
I think it's related to difference of two numbers, a minus b and everything. So if it's spread out, then the difference will become smaller.
Okay, that I don't think that exactly works, to be honest. I'll have to think. Difference is weird, right? Because like difference is like unsymmetric. So you have 3 and 1s. Their difference like you can take as like 2 or minus 2. And like it would be hard to differentiate between them. Sigma function in statistics. Wait, what? Xi minus xi plus. Okay. Wait, that idea might work. Let me just think about that. Yeah, not necessarily, right? The thing is, it's like some like here you had 2 stones, and here you had a million stones, and here you had 1434 stones. So as you spread these two out, the differences actually increase. You have to think of something else. Yes. Okay, so Suredeep, I'll also like write a new problem, but think about my hint. That's related to my last class. How do you formalize what becomes smaller when you spread it out? Okay, let me think of the next. Let me give another problem, by the way.
The product, I guess, becomes larger.
Broad, yes. I think wait. Okay, wait. Yes, but it's actually become small. I'll get back to you. Just give me a second. Let me just write another problem. This time you don't have to deal with my handwriting. I have pasted a problem. Oh God, why is it so small? Okay, just take a screenshot because I'll be moving around the screen a bunch. Okay, the people saying wave functions, just ignore them. Pranav is realizing the Rishal books questions. Shush, shush. Oh, you have already done this problem before. Oh, take a screenshot. I thought you did this problem. Okay, that's fine. Just try this problem. Okay. So yeah, someone said the product. Yes. As you know from the AMGM inequality. Oh, wait. Like root AB is less than equal to A plus B by 2. Right. And like if A plus B is fixed, then like if A and B are equal, this equality holds. If A and B are really far apart, then this equality just like becomes worse. The closer A and B are, the closer the geometric mean is to the arithmetic mean, right?
Yes.
So when you have two numbers, apparently they are both equal. Like we have, like you can just think of the stones as like numbers. So if you have a stone at 5, you write 5. So we have two 5s. We replace it by a 4 and a 6, right? So earlier the geometric mean was like since it was 5 5, the geometric mean was close to the arithmetic mean. Now it's farther apart because the numbers are distant. There is an issue, like you have to like still do work on this argument. Like the main issue is AMGM only works for positive numbers, and there are negative numbers also in our case.
Wait, how are the negative numbers?
Like AMGM doesn't work for negative numbers, right? So
No,
like there is a fix.
How
You
are
can
the
try to.
numbers in this problem? I mean, how can you have negative number of
No,
stones?
stones can be placed at -1.
So how does the number matter?
No, like what what the idea was. Suppose you have like some stones. You have two stones at 5. You have like three stones at 6 or whatever. Suppose you just have this. So you make a list of numbers. You have two stones at 5, so you write 5 twice. You have three stones at 6, so you write 6 thrice. Okay. So now our operation is just you take two copies of the same number, you decrease one, and you increase one. Right.
Yeah.
This is what our process is. Right.
Wait, so can you say that like since the number of stones is staying the same, then if you look at the geometric mean of the stones at each place, and like let's say if you are doing your operation on A and consecutive nu- consecutive number of stones are B and C, then the after doing that step, the geometric mean ABC will change to A minus 2 times B plus 1 times C plus 1.
Mhm.
Like, does this always decrease the GM or something?
Yes. Yes. Because the point. First you had like A and A. Now you have A minus 1 and the A plus 1, right?
Yeah, yeah.
So the product of A minus 1 and a plus 1
Yeah.
is a square minus 1, which is less than a square. In fact, as you might notice, you don't even have to use AMGM. AMGM is how you like intuitively think of the problem, but you have to realize at the end of the day, it's just this. And here we don't care if A is negative or positive, it's just smaller. Use black or red color, okay.
What if we take A and B?
No, you can't, right? The thing is, take a number where two stones are placed. You're taking two copies of the same thing.
Bhaiya, what does iterations mean?
Iterations? Iteration is just like multiple copies of the same thing. Wait, how do I change the color, guys? Help me out here. Oh, okay. That's easy.
Can you please explain what is A here?
Okay. So, let me just explain like the whole solution now from scratch. So, first of all, you stop thinking about the number line. What you do is you instead make a list of numbers. Suppose there were two stones at A, so you write, two stones at 1, you write 1 twice. There were no stones at 2, you don't write any 2 anytime. Suppose there were like 12 stones at 3, you write 3 12 times. Okay? So now you have converted the stones into just a list of numbers, which denotes the positions of the stones. Okay? Now, the claim is that the product of these numbers, like I don't even have to take the mean, I will just take the product. The claim is that the product of these numbers always decreases as we do this process. Is the claim clear?
By the way, here negative number should not be the issue, right? Because we can
negative number. Actually, wait,
Yes,
no, negative
yes.
number.
we can just shift the stones to like the positive side.
That's actually the fix. I'll get to it. Wait. There are some issues. I'll address them. I'm just giving like the big picture argument. Okay. So what is our process? So we take two stones placed at a single value, and like we replace it by a stone at 2 and a stone at 3, 4. And the claim, as I've stated, is not exactly true. I'll explain the issue, but this is the idea. Okay. So in our list interpretation, we have a list of numbers. So we take some number that appears multiple times, say 3 appears multiple times. We erase both instances of 3. We put 1 2 down, we put 1 4 down. Is it clear what like the process is? Like you understand why this list of numbers interpretation is same as the stones interpretation. Now look at the product. So you have a product of a bunch of numbers, A, B, C. No, actually this is bad. A1, A2, all the way to say AN, right? So what we do is we have like in the middle, we have two numbers that are equal because our process only works when we have two equal numbers. Suppose we have X and X in the middle. We replace it by X plus 1 and X minus 1, right? So now what happens to the product? So we still have like everything except X, the product of those remains the same. Earlier we had X squared. Now we are left with X squared minus 1. X plus 1 times X minus 1 is X squared minus 1, which is smaller. Right? So the product of AI, like after doing our moves, it decreases because we have replaced X squared by X squared minus 1. Does everyone like, there's an issue. I'll point out the issue in a minute, but does everyone
I have one
see
thing.
what's happening?
Yeah, I have one thing.
Go on.
Here we are also taking in negative numbers, right? I think that's creates issue. But then
that creates issues.
those
Yes, sir.
take stones.
That fix is correct. I just
That works, right?
basically like just does everyone understand? Then I'll explain why it doesn't work, as he has already pointed out. But does everyone basically understand what I'm trying to do?
Yeah.
Okay. So now the main issue is this inequality isn't true because suppose there's a 0 here, then like it's equal. Doesn't matter if you make this smaller. 0 times anything is still 0 times anything is still 0. Similarly, if there's a minus 1 here, then the equality just reverses. It increases. because you have a smaller negative number, like a number that is smaller in absolute value, but it's negative. Right. So that is the issue. But there's a very simple fix. Well, there are two fixes. Like the more scam fix, actually, no, most fixes are not scams. The thing is, there are finitely many numbers, right? So after some point, there are no numbers at all, right? And the thing is, the values on the number line don't matter, just the positions matter, right? So just move the number line back. Like if 0 was here and we had like some stones here, just shift the number line so 0 is like here and all the stones are at positive places. Is this fix clear to everyone? Just since there are finite numbers, you can just go far enough back and there will be no more stones.
How do we say this in a descriptive exam? Write this in a descriptive.
Yeah, it's hard. That's why I'll use the like slightly weird because there's like how will you use this? Like, okay, here's I'll just give some writing advice. I'll just say how I will write this if this was the proof I'm doing. So I'll say, for the sake of contradiction, assume you can get back to where you started. We should have a class. We'll have a class on write-ups after IOQM probably, like before RMO. There are infinite. But the thing is, no, but most of them will not have anything placed on them. Yeah. For the sake of contradiction, assume you can get back to the starting configuration. So you have some configuration A, you get to B, you get to C, and eventually you get to like, once again, you get to A, right? In all these configurations, since there are finitely many stones, there will be some point like below which they never go. They are always above that point, right?
I have a question related to this.
To the write-up or to the...
No, to the solution, the fix that you told.
Uh-huh.
So we're just moving the number line back enough, right? So that everything
Huh.
becomes positive.
Yes.
So are we doing this in every iteration or just for the first iteration?
Yeah. That's like sort of the reason it's bad to write up. That's what I'm saying. Okay. The thing is, what can happen is that we have made all the numbers positive, but we do a sequence of moves that ends up placing a number at a negative value. That can happen, right? So in a descriptive exam, what you will do is first you say, suppose you can get back to where we started and move the number line so far back so that in all the configurations we take, all the numbers are positive.
Wait, can we take absolute value of the numbers in the like
Absolute value, then the issue is 0. Like,
zero?
sure, absolute value decreases, but if there's a 0 here, it's still smaller.
We may say that
It's still equal.
let's not consider 0 in our number level.
What?
We may not consider 0 in our number level. So like let's just exclude 0, and then
No,
that will only be
you
will
can't
go
just like
to minus
exclude
1.
0 for free. Can you?
I don't know. I mean, it works.
You're saying the product of non-zero. Look. No, that doesn't exactly work because what if we are doing a move on the 0 spot? Then
Yeah,
that doesn't.
I'm saying that let's just not think about 0. Let's say after 1, you directly get -1. And then press this.
Wait, that's hilarious. Okay, that also yeah, that works. Okay, so what he said is just like assume you don't know how counting works, and for our number lines, it's 1, 2, 3, 4, and then -1, -2,
I mean,
so on.
you can have
0 just doesn't exist.
-1 to on the left hand side, right?
What?
Instead of -1, -2, let's just have.
Yeah, also yeah, make this our number line. And it's just like, okay, for anywhere here or here, the product decreases. In these areas, it's like you have to verify. Like if you do a move at 1, then it's like not the same argument, but you can just say, earlier the product was 1 times 1, now it becomes 2 times 1, so it increases. Oh, it increases. That's an issue. Oh yeah, this doesn't work. Never mind. Never mind. This does not work. This seemed very clever, but unfortunately, it doesn't work. Okay, do you understand the issue? But, like just ignore this. I was like trying to see if this idea worked, but it doesn't. Anyway, right. Give me a second. The dog is. Okay, just ignore the last like 2 minutes or whatever. I was trying to. Okay, let's get back. I'll explain why. Just ignore that idea. It's wrong. Unfortunately. Anyway. Okay, so does everyone understand like the idea behind this fix? Like you just move the number line back so everything is positive. Just the idea, not the write-up for now. If anyone has any doubts in the ideas, just ask. Okay, I don't think there are any doubts. Okay, so okay, I will. There's not enough time in the class, so I'll like explain the write-up later, maybe in a future write-up class or in the PSET, whatever. I'll tell you like the fix I like better. Uh, so we have AMGM inequality. Like this is this is what motivated this solution. The issue with AMGM is that it only holds for positive numbers. Negative numbers are causing us an issue. So instead, use some inequality that always holds. For example,
AMGM always works for two
positives.
numbers, right?
No, if it's negative, it doesn't work.
Oh, it's inside the square root, so negative.
Yes. But here's an inequality that always works. Wait, let me just square which side is it? What is the direction? Square. Yeah. Unfortunately, I did not get to cover this in my. This is the AM-RM inequality. The proof for this is like very simple. You expand it out. You expand and you multiply by 4 on both sides. So you get a square plus b square plus 2ab. You want to prove this is less than equal to 2a square plus 2b square. And this is the same as like take everything to that side, 0 less than equal to a minus b square. AMRM, or like this is just like an instance of the power mean inequality. QMAM, yeah. You can also call it QM. So basically the idea is instead of like multiplying the numbers, quadratic mean, just a square plus b square, like the quadratic mean is defined as a square plus b, like you take the arithmetic mean of the squares and then take its square root. So basically, we can finish this yourself, but the idea is instead of like multiplying the numbers, which causes issues with the negatives, you add all the squares. So you say a square plus b square plus c square, and so on. Now, what you do is you replace, yeah. So if you ever have a and a, this becomes a plus 1 and a minus 1, right? So here the sum was 2a square. If you add these up, the sum is 2a square plus 2. So the sum of squares always increases by 2. So it can never get back to where it started. And here, since there is no products, you don't have to worry about 0 or negatives and stuff. The sum of squares always just increases by 2.
And how does this also hold true when you have infinite number of stones? How can
No, because then you cannot define the sum. For infinite numbers, the proof will be a little different. I'm not sure how you'll prove it for infinite numbers, actually.
is it even true? That's what I'm asking.
Is it even true? I don't know. I think it should be true, to be fair. I will have to think about it. Oh, it is true, but it's slightly scam. Don't worry about it. I'll explain it after class, maybe.
Why
Yes,
won't
about
this work for infinite numbers?
the issue is the sum of squares in that case might just be infinity. Like infinity and infinity plus 2 are both the same thing.
Okay.
Okay. Okay. The class is almost like the official time is over, but I'll just like do the last problem I posted. Where did it go? I'll just paste it again. Wait, actually no. I might just put as homework. What is this? No, I want to cover a different problem actually. It's an important idea, so this I'll just put in the preset.
By the way, just to ask, do you have the preset ready right now? I mean, I'm asking this because the preset is already sent after 3 4 days. So can you
Yeah, no, it's not ready. Uh,
okay.
it gets ready as soon as I decide to lock in and make it.
Yeah, that's fine.
Okay. This problem also had a part B, but only part A is relevant for us. Mm, so just read the problem and I'll probably end the class by at least 8:15. This is the last problem of the class. After which I can have some like questions and answers. Today I don't have to like run away after class. I can stay for questions longer. Some people recognize the source of this problem, which is nice. I should mention this. So in the previous problem, I mean, okay, we can just take a screenshot of this problem, and if you just like want to try it out, ignore me. That's also fine. I'll go back to the previous problem and just talk some pedantics. Wait, I can just post this in Discord chat, right? Oh, yeah. Sorry, Zoom chat. Yeah, okay, you can see the problem in Zoom chat as soon as it loads. Yeah. Okay. One thing I'll mention, the thing we did last time, where did it go? Okay, here. Oh, my text size like keeps changing, right? I'm working on like 10 different scales. This idea that we did, like you add up the squares, this is called weighing. Basically, like sometimes like the invariant or monovariant is obvious. You just add up everything, you just multiply everything, then that's just the invariant, right? When you're doing that, like suppose in some problem the invariant is just the sum of all numbers, like the very first example we did. In that case, every single thing is like considered equally, right? All the numbers you just add them up. It's completely symmetric, right? But in this problem, every number was not considered equal. Like any stone that's at like position 1 gets a weight of 1 square, like is added up. Like for any number at position 1, it contributes 1 to the monovariant. Any stone at position 2 contributes 4 to the monovariant. Any stone at position 3 contributes 9 to the monovariant. Any stone at position 4 contributes 16 to the monovariant. Right. So all stones are not considered equally. We call like these things the weights of the stone. Stones at different position are like more valuable than other stones. They weigh more. You can say like a stone at this position weighs 16 kgs, but a stone at this position weighs 4 kg. So like, and the total weight increases, or yeah, increases. Like this idea in general is called weighing. When you're trying to find some invariant, like in a problem that where like the position matters, so you'll usually look for something like summation f of a. In our case, f was just like the function a squared. And this is like called the weighing function. You want to give some sort of weights to every position, such that like the monovariant is actually a monovariant. For example, we use squares, but in general, the way to solve this problem is just like if I see this problem today, what I'll do is I'll think I want a monovariant. So I want like something that increases as I go from xx to x minus 1, x plus 1. So I'll just say, suppose my monovariant is some function of x. Like I'm adding up like summation f of ai over like all the numbers. I'll just try to look for a function such that f of x plus f of x is like either greater than this or less than this, no matter like an increasing monovariant is fine and a decreasing monovariant is fine. I just want some weighing function that does this. And that function here happens to be squares. But there are like infinite weighing functions that work. So usually when you like see some sort of problem in the wild where like the obvious monovariants don't work, you try to think like a monovariant has to be a function. So you see what kind of inequality that function satisfies, and then think of an example instead of just like randomly coming up with like magical looking examples. Was my pedantic yap sort of, did any of that make sense? No reply. Did I bore you all? No, it's not. It's not. I'm just
I was
no.
solving the
What, Keshav? Can you? I didn't hear you. Can you repeat?
No, I couldn't reply because I was solving the other
Oh,
problem.
okay. That's fine. No. Like here in our Nikhil, in like what we did in the end, we said that the sum of squares increases. So any stone at the position 2 contributes the value 4 to the sum of squares. So like in that sense, it's 4 kgs. Kg doesn't matter here, of course. For example, we can use this idea here, like the generalized idea of weights. People who like paid attention to what I was saying, did you understand it?
Yes.
Okay. Okay, 2 people have said yes, so I'll extrapolate from that. If you don't understand that, please just say or message me. Yes, the game. Speaking of which, okay, it's been, I think, 10 minutes. I gave this problem at 8 p.m. So I'll just give some hint. So once again, uh, the answer you should like guess is no, because answer being yes will be really weird. I mean, can be yes, but use the fact that we are covering this in this class. So the answer has to be. So we need to find some like monovariant that always, oh, text suddenly became bigger because I zoomed in. Okay. We have to find some monovariant that always decreases. And since it always decreases, and like use that argument, any decreasing sequence of positive integers must end. Right. So what are we doing? So we have like card 1 all the way to card 2009. and say we suppose like card 1 is gold, card some is like at some position. Yeah, yeah, this is much better. Yeah, at some position, like some cards are gold and some cards are not gold. Yeah, okay. Ayush has said the answer in replies in chat. That is perfectly correct, but I'll try to motivate it a bit more. So what do you want a monovariant? So like, what kind of monovariant will it be? So suppose you like guess that you have to do some sort of weighing. So for every like weigh every position, like you weigh one as like there's some weighing function. So one goes to f of one, two goes to f of two. You don't know what this function is yet, right? And you add this function for every gold card. This, and then you prove that as you do a flip, this sum always increases. This is the kind of thing you're looking for in some sense, right? So ready? Do you understand what I'm saying? You're looking for some kind of function such that like you add it up over all gold cards and it always decreases. Like always decrease, always increases. It's monovariants, it's fine. We'll deal with it. Say always decreases. Okay. Yeah. So you're looking for this kind of function. So what do you want? So what do you do at the animal position? You make the like you make the first some what's leftmost, right? Leftmost of which is gold. Right. So like some number n will be gold and n plus 1 all the way to n plus 49, they'll all be silver. They will all be something else. We don't know. So in some position, like what you do is from summation f of I, where I is gold, you subtract the value of f of n, and we don't know what happens next. Like some of these you might be subtracting, some of these you might be adding, right? Any gold card, any card that was initially gold, like you lose that amount of weight. Like if n plus 1 was gold, you lose f of n plus 1. If n plus 1 was not gold, then you gain n plus 1. F of n plus 1, whatever our weighing function is. It can be squares, it can be just normal, we don't know yet. Right. Yes. But we want this thing to like always decrease, right? So our worst case scenario will be that if everything else was silver, is it gold and silver or what is it like gold and red? Gold and black. Okay, so if everything else was black. So worst case scenario, what happens is we lose f of n and everything else gets added. Fn plus 1 plus fn plus 2 all the way to fn plus 49. Right. We want that even if this happens, our function, the sum, total sum decreases. Correct? Does anyone have any doubts with what I'm saying? Could you move a bit up? Sure, I mean, I'll just...
Oh, yeah, so this looks like exponential stuff. Right?
Yes.
Yeah.
Perfect. Perfect. Okay, but just like before, like, you don't have to figure out what the function is right now. But does everyone understand why I am looking for this kind of function? Like to clarify, I'm looking for some function f such that, well, okay, f is like a n to n function such that, or like not even n, I just need f to be defined on 1 all the way to 2009. And by this, you can guess which year the problem is from, 2009. I want some function such that the following is true. Minus fn, like uh, fn is greater than fn plus 1 plus dot 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 plus fn plus 49. Does everyone understand why having this kind of function will work? This is not an IMO problem, but close enough. I'll tell the source. after. I'll just tell this was after BLM. Okay. Does anyone have any doubts with why is this? No, this is not USMO. I don't think. I mean, I don't think this is USMO. That's not where I took it from. Yeah, I'm feeling a okay. Bye, Nikhil. Yeah, just watch it on YouTube. Ask me if you have any doubts. Yeah, everyone else, do you understand why having this kind of function will work? Yes, got it. If does anyone not understand? If anyone doesn't understand, just speak up or DM me. I understand, but how to think? Yeah, this is the idea. Like the way you think of this. Oh wait, are you asking how to think of a function or how to think of this? Of a function, I'll get. But you understand, like you do all these steps feel natural. Like you look at this problem, you think you need an invariant, so you like consider the most general invariant you can think of, f of x, and you realize this f of x must satisfy this kind of condition, right? This is does everyone see like how you will like once you're like practice enough, how you'll like see this problem and realize you have to come up with this kind of function. Yes, good, good. If anyone doesn't, just once again, don't feel free to ask. I'll need, of course, you will need practice. Like this is not easy to see. This is like, but once you do enough combi problems, this is the kind of argument that will become more natural to you. It's like, do you see a world in which you can do this? anyway, let's get it. So now we need this kind of function. And at this point, the thing is we can just make a function. We just need a function defined on like 1 to 2009, right? So like start at 2009, say 2009 to 2000, like, what's like 2009 minus? One, what is this? 1969. How many numbers are there between this 1969 to? I need might need one nines. No, sorry. 1960. These are 50 numbers, right? 1960 2009. Yeah. So consider 1961 to 2009. Like these are the last 49 numbers. These you don't care about. These you like don't really care about. These can never be FN because like you can use the leftmost card like has to be with. Well, there needs to be 49 cards after leftmost card, so it can't be among the last 49, right? So in these positions, you can like define the function whatever you want. Like, say just call f of all of these is 1, right? What do you would do with 1960? Well, f of 1960 needs to be greater than f of n plus 1 all the way to f of n plus 49. So the sum of all of these is 49. You make f of 60 50. F of 1960. What about 1959? Well, f of 1959 needs to be greater than the sum of 1960, 1961 all the way up to 2008. So that sum will be 99. So you just like, yeah, you just make this 100. Or like you can even make this 1000 or 10,000, doesn't matter. And 1958, it needs to be bigger than the sum of all of these. Just make it a Google. Obviously, it's bigger. 1957, make it a Googleplex. Just pick even obscenely more large numbers than the previous number. And obviously the sum will be greater. Like you don't even have to come up with an explicit function. You can just say, I define this function such that this happens. Just keep picking larger numbers, very large numbers. And this works.
Wait, so here 50, taking 50 numbers or 2009 doesn't really matter anything. They're just,
Yeah, like, of course. In this question, 2009 and 50 are placeholders. Like it matters a bit to part B. Yeah, this is 2009 C, C1. So This is like harder than anything you'll see in a typical RMO. It is a C1. It can be a IMO problem. So don't worry if you don't get it, but like it's very instructive, all these ideas. So you try to okay. I'll cover a different solution of this also, but just bear with me here. Does everyone understand this first? It's amazing. Okay. Does anyone have any doubts with the solution? You try to find a function, you know it must satisfy this, and then you just make a function that satisfies this. Just pick in like insanely large numbers. Any doubts with the solution? Everyone sees why the solution works. Let me just ensure, yes. Okay. I think a bunch of people have messaged me. Yes, if anyone, how many people are left in the meeting? I don't know. I can't check. Anyway, if anyone has any doubts, you can ask right now or how to think. And how to think you will get well. Like this is like the idea. Like whenever you see a problem, you try to come up with an invariant, monovariant. Like this problem is a monovariant problem because you want to end the game. Then you just think of a function, like say there is some monovariant function, and then just try to find all the conditions that function must satisfy, and then just make a function that satisfies these. Okay. Before we end, I'll present like someone, I think it was Ayush. He said like a different solution of this, which is like the more classic solution, which I'll explain when we listen to this. Like, oh my God, I'm being really bad with that, right? Okay. Before 12 a.m. tonight, I'll send us all the slides of all the 3 classes I have taken. I promise. If I don't, just spam ping me in the OMC Discord till I do. Like actually just like start spamming. Is there a pset? There will be a pset. There will be a pset. Yeah, I'm being really lazy with sending the slides. I will do this. Okay. The other solution is this. Take all the cards that are like gold and silver. For every gold and black. For every gold card, write a 1. For every silver card, write a 0. Okay. So you'll get a sequence like initially everything is 1. Then you'll have like sometime you'll have some 1, 0, 1, whatever. And then you have written a sequence of 1s and 0. Just read it off as a number. Read it off in base 10 or read it off in base 2. Does not matter. Just think of it as a number. So in a move, what are you doing? You take some 50 digits and you flip them. And the thing is, since the leftmost digit is a 1 and that becomes a 0, it doesn't matter if these digits increase, the number obviously decreases. Like if the higher place digit decreases, the number decreases. Is this solution clear to everyone?
Yes.
I'll just, is it, okay, more importantly, is there someone who does not understand this? Oh, wait, is class? Let me just check. I'm slowly learning you guys' names. Wait, 10 participants left.
First,
People left. There's some people left, that's fine. Okay, I'll assume everyone understands this. And as you might know, what? Yeah, action.
one question. Yeah. For some reason, the previous solution you showed, I think it makes sense, but then at the same time, it kind of doesn't make sense.
Wait, what doesn't make sense?
I mean, I get the proof and all, I get how constructed.
Yeah.
But I mean, just feels weird, right? How are we do? Meaning, if you think about it broadly in terms of the problem, this is completely unrelated. So,
Like, I think the second solution actually makes the first solution more clear. The
yeah,
idea is that the ones are moving to the right. Like, if you have the one, like, there are less ones on the left side and the right side, and the right side ones are not big enough to compensate the left side. So you just want to like give the left side larger weights and the right side smaller weights. That is what's happening here in this solution also. If you look carefully, this solution is just the previous solution but I have a like explicit formula for f of n. It's just 2 to the 2009 minus 7.
Yeah.
It is the same solution. Like, the point is you don't need to come up with an explicit function, but the idea is the same. You want the left to matter more than the right.
Yeah, that makes
That
sense.
seems like something that can be taken out of context. That's fine. Okay. I agree, like the solution like might seem a little bit magical. Like, how will you come up with this? But do you understand it? Both of them. Everyone. Okay. Yep. Okay. I think everyone understands this. So this was the last problem. I'll send the slides, and oh my god, the slides are like very different sizes. I'll figure out how to send these. I hope you like like okay, there was no theory. So like basic ideas covered are like okay, basic invariant and monovariant. Then like how to come up with more like sometimes you like factorize to get like more complicated stuff. And the like main like heavy duty idea we covered are weights. The last two problems both involve weights. And just like how invariants and monovariants can be used. Okay. That is, well, basically everything for the session. If anyone has any questions, both regarding the lecture or just in general, you can ask. I'll stay here for like some more amount of time till people have questions. I'll stop recording and screen sharing now, though.
This stone problem before, the I think